Good evening, and welcome to the Sleepless Scientist. Tonight's story drifts into one of the most mysterious stages of the universe, the quantum realm. If these calm explorations feel right, you're welcome to like and subscribe. Share in the comments where and when you're listening. It's heartwarming to see our circle. Now relax, dim the lights, and let's quietly set out. If your mind wanders, just let it. We'll still be here. The world feels familiar until you lean very close. You touch the handle of a cup and it feels solid. You hear the tick of a clock and it feels steady. You see the glow of a street lamp outside your window and it seems perfectly ordinary. But underneath those calm appearances, the universe is busy telling a stranger story. Beneath the surface of cups and clocks and lamps is the quantum realm, a realm that doesn't play by the rules we expect. If the ordinary world is like a stage play with actors reciting well-rehearsed lines, the quantum realm is more like a rehearsal room with scripts half written, lines muttered, and outcomes undecided until the curtain rises. What seems simple at our scale, light shining, atoms resting in place, nerves carrying signals, is deep down a restless theatre where possibilities drift like smoke. To enter this theatre is to step into a place where intuition falters. A photon of light isn't just a particle or a wave, but somehow both. An electron in an atom doesn't orbit like a tiny planet, but sways in clouds of probability. And the very act of looking, of observing, seems to change the story being told. It's as if the play rewrites itself, depending on who's in the audience. This is the strangeness of the quantum world. And though it sounds distant, it isn't. It's inside your body right now. The warmth in your fingertips is carried by vibrating atoms, each bound by quantum laws. The glow of the lamp is the journey of photons, behaving in ways that belong to no ordinary category. Even the electrical whisper that travels along your nerves when you reach for the lamp switch relies on the quantum tunneling of ions through channels in cell membranes. The strangeness is not elsewhere. It is here, woven into the texture of your own experience. The quantum realm isn't another universe. It isn't a place with a boundary you can cross, like stepping from land to water. It is instead the foundation of everything familiar, the rules written in ink so fine that we only notice them when we build instruments sensitive enough to magnify whispers into voices. For centuries, humanity lived without hearing this hidden chorus. Only in the last 100 years have we tuned our ears to the music beneath the noise, and what we found was unsettling. The universe, so long described as predictable clockwork, revealed a different face, one made of uncertainty, duality, and entanglement. The more carefully we looked, the more the rules bent, until the very act of measuring seemed to become part of the play itself. It was as though reality had been waiting for us to ask, and only then chose an answer. But don't worry. Tonight we're not here to solve equations or master abstractions. We're here to drift slowly through this landscape, to feel the wonder rather than conquer it. You don't need to carry the heavy pack of mathematics on this walk. All you need is curiosity, and perhaps the comfort of knowing that the very mysteries that baffle physicists are the same ones that let your lamp shine, your clock tick, your cup hold warmth. So imagine yourself standing at the edge of a quiet forest at dusk. You know the path leads inward, but you cannot see where it goes. The air is calm, but the shadows are shifting. That is how the quantum world feels. Inviting, but elusive. Every step takes you deeper into uncertainty, yet each uncertainty is strangely beautiful, like mist curling through trees. As we begin this journey, think of the quantum realm not as a problem to solve, but as a companion to wonder with. Each principle, wave-particle duality, superposition, entanglement, uncertainty, will appear not as a lecture, but as a character in the story. They will step forward, introduce themselves, bow, and then retreat into the haze, and around them new figures will emerge, exotic forms of matter, clocks that measure time with unimaginable precision, biological processes that borrow quantum tricks, and bold speculations that place consciousness itself inside the script. If at times your thoughts drift, let them. That is the nature of quantum mechanics too. A drift, a haze, a blur of probabilities. If you close your eyes, the story will still unfold. If you fall asleep, it will continue without you, the way particles evolve even without observers. You may awaken later and find that you missed a chapter, but like all quantum stories, the traces will linger, ready to be pieced together. There is no hurry. The atoms beneath your skin have been playing this game for billions of years. Tonight we're only pausing long enough to notice. So here is the invitation. Step closer, soften your gaze, and let the theatre beneath reality open its curtains. For the next while, we'll move gently across its stage, seeing how it shapes the familiar world, how it whispers through plants and stars, and how it may, in ways still debated, need us to listen in order for the play to go on. And if, in the end, you're lulled into rest by these strange tales, perhaps that is fitting. After all, in the quiet borderlands between waking and sleep, we are ourselves in superposition, half here, half elsewhere, until morning decides. If you have ever tried to sketch a map of a place you've never been, you'll know the odd combination of excitement and confusion that comes with it. Your pencil hovers above the paper, you draw lines for rivers and paths, but in truth, you're only guessing, building an outline of something you have yet to walk. That is not far from how physicists feel when they talk about the quantum world. For centuries, we had maps that worked beautifully. Newton's map was a proud example, a universe that moved like a grand machine, each gear turning with precision, each cause followed faithfully by its effect. It was a clockwork cosmos, steady enough to predict the rise of tides and the swing of planets. People trusted this map because it seemed to match the world of apples falling from trees and cannonballs tracing arcs across the sky. And then came the quantum realm, a landscape that shrugged at the old cartographer's tools. Newton's rulers and compasses, which had drawn such neat lines, suddenly felt clumsy, too blunt for the fine grain of reality. Instead of steady planets, we met particles that could be waves. Instead of a clock with sure hands, we met probabilities, smudges of possibility. Trying to map this was like trying to chart a coastline made of fog. Each step you take changes the shape of the shore. Einstein, for all his brilliance, struggled with this. He had given us relativity, a new map that bent space and time themselves, yet even he wanted the comfort of certainty. He once said that God does not play dice, expressing his doubt that randomness could be fundamental. But the experiments whispered otherwise. The dice were not just rolling. They were rolling in a way no hidden hand could predict. The map was not simply incomplete. It was a different kind of thing entirely. To picture this gently, imagine standing before a pond at dawn. Mist rises from the surface and you can only just see the water underneath. If you throw a pebble, ripples spread out, but the mist blurs their shape. You know the ripples are there. You feel them with your eyes half closed, yet you cannot mark their boundaries with a ruler. That is what it means to step into the quantum pond. You can sense the ripples of probability, but the mist of uncertainty hangs over them, softening edges, refusing to be fixed. This refusal, strange as it may sound, is not a flaw. It is part of the design. The quantum world does not lack clarity because we are clumsy observers. It withholds clarity because clarity in that realm does not exist in the way we think it does. There are no tiny marbles hiding beneath the microscope, no clock springs waiting to be wound tighter. There are only clouds of chance, shapes of likelihood, stories waiting for an audience. That might feel uncomfortable at first. We like maps. They help us know where we are. But sometimes, wandering without a map opens a different kind of understanding. Think of the first time you explored a new neighbourhood without checking your phone. You notice the texture of walls, the sound of traffic, the warmth of light in kitchen windows. You may not know the exact grid, but you come away with impressions more vivid than any satellite image could give. The quantum realm asks us to do the same, to walk without insisting on coordinates, to listen to the murmurs rather than demand exact instructions, and there is a kind of relief in that. The Newtonian map, for all its usefulness, carried a hidden weight: determinism. If everything is mechanical, then in principle every moment of your life is fixed, written in the equations like ink on paper. The quantum map, or rather the absence of one, loosens this grip. It suggests that uncertainty is not a defect, but a space for freedom, a space for creativity. When a photon chooses a path only when observed, when an atom hovers between states, the universe itself is pausing, holding breath, waiting for the story to be told. Of course, physicists still draw their charts and write their equations, but even they admit these are not maps in the old sense. They're guides to probability, not guarantees of place. A particle's wave function is not a dot on a grid, but a soft cloud of maybes, like the blur of fireflies in a summer garden. You cannot say which blade of grass they will land on. You can only say the meadow glows here more than there. This is why many descriptions of quantum theory come wrapped in paradoxes. The language strains, because we are used to maps with lines, not clouds with whispers. Some say quantum mechanics is not a theory of what is, but of what can be asked. The answer is not written until the question is posed. It is like a library where the shelves are invisible until you open the door to a particular aisle, and only then do the books slide quietly into place. You may be wondering, how can such an unsteady landscape give rise to the solid world we know? How does a fog of probabilities produce the reliable tick of your kitchen clock, or the trustworthy firmness of the floor beneath your feet? That is part of the mystery we will return to later. How the fragile rules of the quantum realm build the sturdier patterns of the classical world. For now, it is enough to accept that the strangeness does not cancel out the familiar. Instead, it underlies it, like the roots of a tree hidden under soil, unseen yet holding everything upright. So tonight, as we set off further into this hidden terrain, imagine that you carry no map, only a lantern. The lantern does not show you the whole forest, only a circle of light ahead. That circle is enough. Step by step the path reveals itself, never too far in advance, never too clear. It is not a failure of the lantern. It is the way the forest wishes to be walked, and in that way, the quantum realm invites us to change our expectations. Instead of demanding a full chart, we are asked to take part in the unfolding. We walk, the path appears. We look, the outcome forms. The play is written not beforehand, but as it is performed. The map, if we can call it that, is drawn in chalk upon water, dissolving even as we read it. And yet here we are, still walking, still marvelling, still able to sip tea and hear clocks, knowing that beneath every ordinary moment is a landscape that no cartographer can capture, but that every one of us inhabits. Imagine for a moment that you are standing by the sea, watching waves roll in and break upon the shore. Each wave is wide, spreading its energy across sand and stone, never choosing a single path. Now imagine holding a pebble in your hand, firm, definite, and discrete. Waves are broad and continuous. Pebbles are solid and particular. For most of history, people believed light must be one or the other. Some argued it was a stream of particles racing like pebbles hurled from the sun. Others said it was a wave, rippling across invisible oceans of ether. Both views seemed plausible, yet each clashed with the other. Then, in the 20th century, experiments whispered something far stranger. Light is both. Depending on how you ask the question, it behaves like a wave or like a particle, and sometimes it seems to keep both masks on at once, only removing one when we insist on looking too closely. The most famous demonstration of this is the double-slit experiment, a phrase that sounds dry but tells one of the most magical stories in science. Picture a wall with two narrow openings and another screen behind it to catch whatever passes through. If you shine light through one slit, the screen glows in a simple band, just where you would expect the photons to land. If you shine through two slits and think of the light as particles, you might expect two glowing bands. But what appears is a whole pattern of bright and dark stripes, fringes like those you see when waves on water overlap. Light in this setting seems to be a wave, interfering with itself. So far, so strange. But the tale deepens. Imagine turning down the light so low that photons pass through one at a time. Each photon should, you might think, behave like a tiny pellet, choosing one slit or the other. At first, the screen shows random dots, scattered with no clear design. Yet as more photons arrive, the same wave-like interference pattern begins to form. Each solitary particle contributes to a whole design, as if it somehow spread out, passed through both slits, and interfered with itself before landing. What is a photon then? A particle? A wave? It seems to be both, or perhaps something that is neither. Something deeper that only looks like a particle or a wave when forced into our categories. The act of observing, the way we frame the question, seems to decide which mask it wears. It is as if light were an actor with two costumes, choosing the one that matches the script we hand over. And this is not confined to light. Electrons, those tiny carriers of charge inside atoms, perform the same double act. When fired toward the slits, they too create interference patterns, behaving like waves of probability. But when you place detectors to check which slit they go through, the pattern vanishes, replaced by the simpler result of particles choosing sides. Observation rewrites the performance. The story rearranges itself in real time. To soften this into an image, imagine you are reading a book that changes its plot depending on whether you peek ahead at the ending. If you resist the temptation, the story unfolds with twists and overlaps, characters appearing in multiple roles. But if you glance ahead, the book snaps into a single, linear tale, characters pinned down to one fate. The wave-particle duality is a book that refuses to be one story until you insist. Among the more whimsical extensions of this strangeness is an experiment sometimes called the quantum Cheshire cat, named after the grinning cat in Alice's Adventures in Wonderland. In Lewis Carroll's story, the cat can fade away until only its smile remains. In the quantum version, researchers arrange conditions so that a particle's property, say its spin or polarization, seems to travel separately from the particle itself. Like the Cheshire cat's grin lingering after the body is gone, the quality can be measured in one place while the particle appears elsewhere. It is a playful but profound reminder that our ordinary categories of thing and attribute may not hold steady in this realm. This raises a deeper question. Are waves and particles real, or are they simply metaphors our minds use to grasp something that is, in truth, beyond either category? Perhaps what exists at the quantum level is neither pebble nor ripple, but a subtler entity, something that only shows different faces when we shine our lanterns on it. The philosopher Niels Bohr called this complementarity, the idea that wave and particle descriptions are not rivals, but complementary windows into a reality that cannot be fully captured by either alone. Think of a person you know well. To one friend they are a colleague, to another a sibling, to another a confidant. Each view is true, but no single description exhausts who they are. The quantum world might be like this. A photon is wave to one experiment, particle to another, and something larger than both when we step back. It can feel unsettling to think that reality refuses our neat boxes, but there is also a quiet beauty in it. The universe is not locked into one costume, not limited to one metaphor. It plays with possibility, shimmering between roles, and in that shimmering lies the possibility for everything else. Atoms, chemistry, even the thoughts drifting through your mind now. When you sip a cup of tea, the warmth you feel is the dance of photons radiating into your skin. They carry both the precision of particles and the spread of waves. When you listen to the hum of music at night, the vibrations that reach your ears are born from this same dual nature. Every sense you have, every breath of warmth, every flicker of sight, owes its existence to this refusal of reality to be just one thing. And so, wave-particle duality is not a puzzle set far away. It is the quiet double life of the world you inhabit. It is light pouring through curtains. It is electrons coursing through the device you're using now. It is the smile of the Cheshire cat stretched across the page of reality. Both wave and particle, both ripple and pebble, both storylines at once. The universe, it seems, is content to hold the tension, to balance on the edge of contradiction, until we look closely and ask it to decide. Picture yourself standing in the kitchen at the end of a long day. You open the cupboard, see rice, see pasta, see bread, and you hesitate. In that pause, before you choose what to cook, every possibility seems alive. Dinner is rice, dinner is pasta, dinner is bread, all at once in the quiet imagination of your mind. Only when you reach for the pot, light the stove and commit does one meal become real. The others dissolve, slipping back into the shadows of what might have been. This gentle moment of indecision is not unlike the way the quantum world moves. Particles at that scale do not always sit firmly in one place or another. Instead, they exist in what physicists call superposition, a delicate overlap of possibilities, like melodies played together. An electron in an atom may be in one energy state or another, but until it is measured, it is not forced to pick. It rests in both, or rather, in a mathematical blend that contains both as potential notes. The most famous parable for this is Schrödinger's cat, a thought experiment more whimsical than cruel, though it sounds unsettling at first. Imagine a cat sealed in a box with a device triggered by a quantum event, say the decay of a single atom. If the atom decays, the device releases poison and the cat dies. If it does not decay, the cat lives. Quantum rules say that until the atom is measured, it is in superposition, both decayed and not decayed. So the cat too is both dead and alive, at least in the strange logic of the box. Of course, in practice we do not find such half-cats in the world. The thought experiment was meant to highlight how absurd quantum rules sound when scaled up. But it also makes a point. Superposition is real at the atomic scale, and it takes an act of observation to collapse the haze into one clear outcome. What may seem like a mind game, however, turns out to be nature's hidden advantage. Plants, for instance, appear to use superposition in the delicate act of photosynthesis. When sunlight strikes the leaf, the energy does not march straightforwardly down one path. Instead, it spreads like a wave across many routes at once, sampling possibilities, finding the most efficient way to reach the chemical centres that convert light into fuel. Superposition, in this case, is like water, flowing down every groove of a hillside simultaneously, sensing which channel is smoothest, then sending the whole stream that way. This trick may explain why photosynthesis is astonishingly efficient, far more than our best solar panels. And the phenomenon is not confined to life. In laboratories, researchers have coaxed larger and larger systems into states of superposition. Tiny mechanical resonators, silicon beams thinner than a human hair, or aluminum drumheads invisible to the naked eye, have been cooled and manipulated until they vibrate and do not vibrate at the same time. Entire trillions of atoms in a single device, holding two incompatible rhythms at once, like a drum that both beats and remains silent. These experiments push against the edge of our intuition, showing that superposition is not just a trick of particles, but a potential feature of larger matter waiting to be discovered. What does it feel like, this many-at-once existence? Imagine listening to an orchestra tuning before a performance. Each instrument plays a different note. and in that messy overlap you hear chords, dissonances, layers of possibility. Then, when the conductor raises a hand, they fall into one melody, one decision. Superposition is the orchestra in its tuning phase, holding within it many paths, many songs, until the baton falls and one harmony emerges. There is a temptation to ask where the particle really is during superposition. Is the electron here, or is it there? The answer, strangely enough, is not either. It is not that the particle is in both places like a ghost, nor that it flickers rapidly between them like a faulty light bulb. It is rather that the question of location is premature, like asking what the ending of a story is before the book is finished. Until you read, until you measure, the ending exists only as possibility, not as fact. This quality gives quantum mechanics its air of dreaminess. Superposition is not unlike dreaming, where you may find yourself flying and walking at once, talking to a friend who is also a stranger, living through contradictions that make perfect sense while they last. Dreams only resolve into clarity when you wake, just as quantum states only resolve when observed. Both realms suggest that ambiguity, far from being a flaw, is a natural state of being, and ambiguity can be fertile. In technology, we are learning to harness it. Quantum computers, which we will explore more deeply later, rely on qubits that live in superposition. Each qubit is both 0 and 1 at once, holding an orchestra of possibilities. When many qubits join, the symphony grows vast, exploring countless routes at the same time before collapsing into an answer. It is as if you could try every recipe in the cupboard at once and then, in an instant, sit down to eat the best one. For us living at human scales, superposition is invisible. Our world has chosen its paths already, resolved into cats that are alive or not, dinners that are rice or bread, lamps that are either on or off. But beneath that certainty, the fuzziness persists. Every breath of air, every flicker of light, carries within it the story of many states collapsing into one. The world you know is born again each moment from the haze of quantum possibility, a steady miracle repeated silently in every atom. So when you pause tonight, perhaps with a book in hand or a cup of tea cooling nearby, imagine that in that pause you too are in superposition. Part of you awake, part of you drifting, part of you pondering, part of you letting go. It is only when sleep comes, collapsing the possibilities, that one outcome will be chosen. Until then, you're hovering in the soft haze, many states in one moment, perfectly at home in the quantum realm. If you have ever sat quietly with a close friend, you know the feeling of connection that needs no words. A glance across the table, a shared silence on a walk, and somehow you know what the other is thinking, or at least what they're feeling. Human closeness can sometimes feel faster than speech, as if emotions themselves had leapt across the gap. Quantum entanglement is stranger still, but it carries the same flavour of intimate connection. Entanglement begins when two particles are born together, or interact in such a way that their properties become linked. Afterward, no matter how far they travel, their stories remain entwined. Measure one, and you instantly know something about the other. If one is found to spin up, the other will be spin down. If one carries a certain polarization, the other mirrors it. Einstein, who admired precision above all else, shook his head at this. He called it spooky action at a distance, as if the universe were cheating, letting particles whisper to each other faster than light could carry a signal. For decades, physicists argued whether this was truly real or just an illusion of incomplete knowledge. Perhaps, they thought, the particles carried secret instructions all along, like two exam papers prepared with the same answers in advance. The question remained unsettled until John Bell, a physicist with a sharp mind and a patient manner, devised a way to test it. Bell's inequalities, as they're called, offered a line in the sand. If particles behaved according to hidden instructions, their measured correlations would fall within certain limits. If they were truly entangled in the quantum sense, the correlations would break those limits. And break them they did. Repeated experiments with photons and electrons and ions showed patterns too strong to be explained by hidden variables. The universe was not slipping crib notes into the particles' pockets. It was allowing correlations that seemed instantaneous, no matter the distance. Entanglement was not only real, but woven into the fabric of quantum mechanics itself. Imagine rolling 2 dice on opposite sides of the world and finding every single time that their numbers matched perfectly, not just once or twice, but always, even when you change the rules mid-roll. That is the kind of unshakable connection entanglement implies. It is not communication in the ordinary sense, not a message passed between particles, but rather a deep sharing of identity. They are not 2 independent dice, but facets of the same underlying whole. This isn't just theory. In 2017, Chinese scientists used a satellite called Micius to demonstrate entanglement across more than 1,000 kilometers. Photons beamed to distant ground stations remained correlated, as if the sky itself were a transparent thread tying them together. It was the first large-scale proof that entanglement can stretch across earthly distances, raising the possibility of communication systems that are unbreakable. In quantum cryptography, entangled particles can form keys that collapse if anyone tries to intercept them, making eavesdropping impossible without leaving a trace. Entanglement even shows up inside matter itself, in places as tiny as the heart of a proton. Researchers studying the quarks and gluons that make up protons have found signs that entanglement links these constituents in subtle ways. The building blocks of matter are not isolated bricks, but interconnected whispers, each part aware of the others in ways we are only beginning to detect. To make sense of this in a gentler way, think of music. A single violin note is beautiful, but when joined with a cello and a flute, the harmony is more than the sum of its parts. Entanglement is like that harmony, but instead of notes blending in air, it is properties blending in existence itself. The particles are not independent musicians. They are a duet written into the score of reality, inseparable even when played apart. What does this mean for us? On one hand, it shows that the universe is less like a collection of separate objects and more like a web of relationships. On the other hand, it challenges our sense of locality, the idea that only nearby things can influence one another. In entanglement, distance becomes almost irrelevant. Particles can be oceans apart yet still share a fate. But before we leap to conclusions about faster-than-light communication or psychic links, it is important to note, entanglement does not let us send signals in the usual sense. It preserves correlations, not conversations. It is as though 2 coins are flipped in different cities, and while each lands unpredictably, the results always mirror each other. You cannot use that to send a message, but the pattern itself is undeniable. The universe is not whispering secrets, but it is humming a duet. Some philosophers and scientists have taken entanglement as a hint that information itself may be more fundamental than matter. If particles are defined by the correlations they share, then perhaps the universe is not built of things but of relationships, a fabric of connections from which things emerge as patterns. This view, still debated, has a quiet elegance. It suggests that at the deepest level the world is less about isolated dots and more about the lines that bind them together. It may sound abstract, but there is comfort here too. In a way, entanglement mirrors our own experience of being alive. You're not simply a lone individual. Your thoughts and moods shift with those you love. Your actions ripple into the lives of strangers. Your existence is laced with unseen threads of influence. The universe, it seems, operates the same way, carrying hidden harmonies across unimaginable distances. So next time you sit with a friend and find that you both laugh at the same moment, or you both fall silent without needing to agree, imagine the particles deep inside you nodding in recognition. They have been entangled with one another since the dawn of time, carrying patterns of connection as old as the stars. Entanglement is not just physics. It is a reminder that even in the vastness of space, nothing is ever truly alone. There is a comfort in clarity. A well-written sign on a street corner, a sharp photograph of a familiar face, the clean tick of a clock that announces each second with precision. These things reassure us that the world can be measured, that certainty can be found if we only look carefully enough. Yet in the quantum realm, certainty itself slips away, not because our tools are too clumsy or our eyes too weak, but because the world is woven from uncertainty at its core. This is the heart of Heisenberg's uncertainty principle, one of the most famous and most misunderstood ideas in all of physics. In its simplest form, the principle says this: there are pairs of properties that cannot be known with unlimited precision at the same time. Position and momentum are the most famous pair. You can know where a particle is, or you can know how fast and in what direction it is moving, but the sharper you measure one, the fuzzier the other becomes. It is not a matter of experimental error or hidden detail, it is baked into reality. The particle does not have a perfectly defined position and momentum simultaneously. Its being is a blur, a cloud of possibilities. To soften this into an image, imagine trying to photograph a dancer in motion. If you use a very fast shutter speed, you can freeze her at a precise point, the arc of her arm, the bend of her foot, but the sense of her movement is lost. If you use a slow shutter, you capture the sweep of her dance, a blur that reveals speed and rhythm, but her exact position is hidden inside the motion. Both photos are true, yet each excludes something. That is the nature of quantum measurement. The world offers one kind of clarity only by withholding another. At first glance, this might seem like an irritation, as if the universe were teasing us by keeping some of its cards hidden. But the truth is stranger and gentler. Without this uncertainty, the universe as we know it could not exist. If electrons could have perfectly precise positions and momenta, they would collapse into the nucleus of atoms, like moths rushing headlong into a flame with no resistance. Chemistry would unravel, matter would dissolve, and the stable structures we rely on, wood, stone, bone, breath, would vanish. The uncertainty principle holds electrons in their diffuse clouds, preventing collapse, allowing atoms to stand as the building blocks of stars and life. Think of it as a violin string, always vibrating. If the string could be perfectly still, frozen in certainty, there would be no sound. But because it trembles, the music exists. Uncertainty is that trembling woven into the universe, ensuring that things remain dynamic, alive, and capable of harmony. The very instability is what makes stability possible. There is also a philosophical depth here. The uncertainty principle reminds us that knowledge has edges, not because we are lazy, but because nature is subtle. To know is to accept limits, and within those limits lies the richness of possibility. When you look at a horizon blurred by morning mist, you may not see every tree, every blade of grass, but the haze itself gives the landscape a dreamlike beauty. Likewise, the quantum haze is not a failure of vision. It is the fabric of reality, shimmering between clarity and mystery. In experiments, this plays out in ways both precise and poetic. Electrons in atoms occupy orbitals not as paths, but as probability clouds, shimmering regions where they are likely to be found. The uncertainty principle defines the very size of these clouds, which in turn define the size of atoms, the bonds of molecules, the shapes of crystals. Look around your room, the chair, the book, the glass of water on the table. Their solidity depends on electrons refusing to be pinned down. Without uncertainty, there would be no space between things, no bonds to hold them, no matter at all. Even stars owe their lives to this principle. In the hearts of dense stellar remnants, white dwarfs and neutron stars, uncertainty takes on the form of what physicists call degeneracy pressure. Electrons and neutrons cannot be squeezed into the same state, and uncertainty ensures they resist being packed too tightly. This resistance is what allows white dwarfs to shine quietly for billions of years without collapsing under their own weight. Uncertainty in this cosmic theatre is not weakness but strength, the silent scaffolding that keeps stars from imploding into black holes. We might also think of uncertainty as a kind of generosity. Instead of demanding that the universe be one way and only one way, it allows space for alternatives, for fluctuations, for surprises. Life itself thrives on that looseness. If everything were predetermined down to the last decimal, novelty would be impossible. But because reality is blurred, there is room for chance, for creativity, for outcomes that could not have been predicted. Perhaps you have felt this in your own life. A conversation drifts in a direction you did not plan. A chance meeting alters your path. A moment of hesitation opens a door you never expected. The uncertainty principle is not only a rule of particles, it is a reminder that even in physics, the strictest of sciences, openness is written into the code. The blur is not an obstacle to meaning, it is the condition for it. So tonight, as you lie back and let your thoughts wander, imagine the electrons in the atoms of your pillow, hovering in their shimmering clouds. They are not fixed like marbles, but restless and indeterminate, held in place by the very impossibility of being pinned down. The comfort you feel, the softness beneath your head, the breath in your chest, all depend on this productive blur. The universe is not built on certainty, but on a haze that cradles stability, a mist that holds the solid ground beneath your feet. And within that mist, the music of existence plays on, quiet, steady, and beautifully unresolved. You may have heard the old saying that a watched pot never boils. It is, of course, an exaggeration. Pots do boil, whether or not you stand by the stove with anxious eyes. Yet in the quantum realm, there is a version of this proverb that holds true. Observation itself has power, not the power of will or desire, but the power of measurement, of attention written into physics. Watch closely enough, and the story changes. This is the essence of the observer effect, one of the most unsettling ideas in quantum mechanics. At its core, it tells us that the act of measuring a system forces it to choose an outcome. The electron that was a hazy cloud of possibilities sharpens into one location. The photon that wandered in superposition picks one path. Before the observation, the world is written in maybes. Afterward, the page has a line inked in. In everyday life, we take it for granted that things exist whether or not we look. The chair is still in the room even if you turn away. But at quantum scales, the boundary between potential and actual seems to rest on whether the system is touched by observation. One of the most curious demonstrations of this is called the quantum Zeno effect. Imagine an unstable particle, one that normally decays into something else after a certain average time. Left alone, it follows its probability, like a candle with a wick burning down. But if you measure it constantly, checking and checking, the act of repeated observation slows the process. It is as if the particle, caught in the spotlight of your gaze, hesitates, refusing to move forward. The saying becomes physics. A watched particle really cannot boil. This effect has been observed in laboratories with atoms and ions, where repeated checks stretch lifetimes like taffy. It is not that measurement freezes time, but that the system cannot evolve freely while being forced to reveal itself. To soften this idea, think of a child practicing a song. On the piano, left alone, she plays fluidly, making mistakes but moving through them, letting the music carry her forward. But when someone hovers behind her shoulder, watching each note, she may falter, restart, hesitate. The act of scrutiny reshapes the performance. The quantum world, though it lacks nerves or self-consciousness, behaves in something like this way. To observe is not passive, it is participation. And then there are the delayed choice experiments, devised to ask a question so odd it sounds like a riddle. Can a measurement made in the present affect the outcome of something that has already happened? John Wheeler, the physicist who proposed them, imagined a version of the double-slit experiment where the decision to measure whether a photon behaves like a particle or a wave is delayed until after it has passed through the slits. Strangely enough, the results suggest that the choice made later still determines the behaviour earlier. It is not that the past changes in the conventional sense, but that the photon never fully committed to one story until the entire experiment, including the delayed choice, was complete. Think of it like reading a mystery novel where the ending determines what clues mattered all along. You reach the final chapter, discover the culprit, and suddenly events from earlier in the book acquire new meaning. In some interpretations, the photon's past is shaped by the measurement's present, as though the novel was written backward, only becoming consistent once the last page is turned. The universe, it seems, may not draw sharp lines between before and after at the quantum level. This does not mean time machines or rewritten histories, though such ideas capture the imagination. It means that reality at its smallest scales is not a fixed film strip, frame after frame waiting to be projected. It is more like a performance unfolding with feedback from its audience, where the story is finalised only when the curtain falls. The act of watching, of asking, becomes part of the script. There is a humility in this, unsettling, but also tender. We like to believe we are detached observers, able to stand at a distance and see the world as it is. Quantum mechanics whispers otherwise. To measure is to touch is to alter, and to alter is to participate. The stage does not remain unchanged when we take a seat in the theatre. Our very presence shapes the play. And yet, this is not a call to despair or to magical thinking. It is simply a recognition that reality is relational. A photon does not wear its particle mask or its wave mask until the world, through an experimenter's hand, asks it to. An unstable atom does not decide when to decay until the gaze of measurement nudges it. The rules are precise, the mathematics exact, but beneath the symbols is a story about how being observed and being real are entangled in surprising ways. If this all feels slippery, that is because it is. The observer effect and delayed choice experiments do not yield easy metaphors. They are like dreams that resist retelling, coherent when lived but fragile when spoken. Still, we can lean on softer images. Think of a painting that changes colours under different lights. Under sunlight, one pattern appears. Under candlelight, another emerges. The painting itself contains both, but which one you see depends on how you illuminate it. In the same way, the quantum realm waits with palettes unchosen until the light of observation selects a hue. So tonight, as you listen in the quiet, you're also participating in countless acts of quantum selection. The photons that strike your eyes have already chosen paths. The electrons in your body have already resolved their positions, all because they are enmeshed with the web of the wider world. Reality has already collapsed into the story you inhabit, but beneath it, at every instant lies the shimmering potential of what might have been, waiting in silence until someone somewhere decides to look. Most of the time, matter behaves in ways that feel familiar. Solids are solid, liquids flow, gases drift and spread, and plasma glows in the sun and in neon signs. These are the phases we learn in school, the ones that guide us as we pour water into a glass or warm our hands at a fire. But when the quantum world takes the stage, matter can slip into stranger costumes, forming phases that feel almost like moods rather than substances. These phases are delicate, difficult to summon, and yet they hint at possibilities more resilient than anything we're used to. One such phase is the excite and condensate. The word may sound intimidating, but it begins with something quite simple. The meeting of an electron and its positive partner, called a hole. In a semiconductor, electrons can be lifted from their usual spots, leaving behind vacancies. These vacancies act almost like positive charges, chasing after their electron counterparts. When an electron and a hole pair up, the duo is called an exciton, a fleeting partnership bound by attraction. Normally excitons are short-lived, like sparks that glow and vanish. But under the right conditions, low temperatures, careful arrangements, excitons can link together, forming a collective state. Many excitons acting in unison create what we call an exciton condensate, a new phase of matter where particles stop acting like individuals and begin behaving as one. To picture this without the jargon, think of a crowded dance floor. At first, each person moves to their own rhythm awkwardly or gracefully but separately. Then imagine a song begins that is so powerful it sweeps everyone into the same motion. Arms rise together, feet strike the floor in unison, the crowd becomes one body. That is the exciton condensate, 1,000 small motions melting into a single coordinated flow. It is fragile, yes, but also strangely sturdy, a reminder that harmony can be stronger than chaos. Another strange phase is the quantum liquid crystal. Ordinary liquid crystals are familiar from the displays in phones and televisions, materials that flow like liquids but maintain some order like crystals. They are useful because they can be nudged into aligning their molecules with electric fields, shifting colours and light. Quantum liquid crystals are their stranger cousins. They arise not from ordinary molecules, but from the collective dance of electrons themselves. In these phases, electrons form patterns that ripple and shift, like liquids that remember being solid, or crystals that have decided to loosen their grip. To imagine them, picture a pool of water where ripples freeze in place for a moment, forming a lattice of standing waves. Then the waves begin to slide, to flow, yet traces of the order remain. The water is liquid, yet it holds the ghost of a pattern. That is how a quantum liquid crystal behaves. It is a mood of matter, halfway between flowing and frozen, flexible yet still carrying memory. What makes these phases fascinating is not only their beauty but their resilience. Some exciton condensates and quantum liquid crystals can withstand disturbances that would normally disrupt fragile systems. They are self-sustaining, radiation hard, like dream materials that continue even when poked or prodded. In a universe where most delicate things crumble under pressure, these phases seem to thrive on strangeness, using quantum rules to create order from the chaos of uncertainty. It is tempting to see them as metaphors for the human condition. We're often told that strength lies in solidity, in being unchanging like a rock. But sometimes, the greatest resilience comes from being fluid yet ordered, from moving together rather than standing apart. The exciton condensate, the quantum liquid crystal. They remind us that even at the smallest scales, harmony is a source of endurance, and that moods, not just materials, can shape the future. In laboratories, these phases are not easy to summon. They require cold temperatures, precise arrangements, and patient observation. Scientists coax them into being with lasers, with magnetic fields, with carefully designed materials. When they appear, they are fleeting, fragile. Yet each glimpse is like seeing a new colour in the spectrum of matter, one that had been hiding all along. And as techniques improve, the hope is that these strange moods will become tools, materials that resist radiation in space, systems that hold memory without wires, technologies that harness coherence instead of brute force. Imagine a spacecraft shielded not by layers of heavy metal, but by materials that shrug off cosmic rays. Imagine circuits that heal themselves, flowing like liquid yet patterned like crystal. Imagine data stored not in fragile silicon chips but in harmonies of electrons, humming together like choirs that do not forget their song. These are not yet here, but they are hinted at in the laboratory, glimpses of futures that quantum matter suggests. To sit with this thought is to realise how alive matter can be. Not alive in the sense of breathing or thinking, but alive in the sense of being capable of moods, of shifting personalities. At one temperature, electrons behave like loners, scattering apart. At another they gather, forming patterns, condensates, crystals that are both liquid and solid. The boundary between matter and metaphor blurs. The universe, it seems, is not content with only 4 phases. It composes symphonies of phases, each with its own rhythm, its own resilience. So tonight, as you rest, think of the matter around you, the chair, the pillow, the air. Beneath their familiar faces, they carry the potential for stranger moods, phases that dance only under special lights, in hidden laboratories, at temperatures close to absolute zero. The world is richer than it appears, and in that richness lies a promise that even the most ordinary materials can harbour extraordinary secrets, waiting for the right moment to unfold. If you have ever watched a spider spin its web, you know the delicacy of threads stretched between branches. A single thread seems almost invisible, yet when woven together, they form a structure strong enough to catch the weight of an insect, flexible enough to survive wind and rain. Entanglement in the quantum world works in a similar way. It is not a glue in the ordinary sense, not a sticky substance you can touch, but a binding of relationships that hold systems together in ways stronger than the parts alone. Without entanglement, the quantum world would be a collection of lonely particles. With it, the world becomes a fabric, interlaced and resonant. In recent years, physicists have come to see entanglement not just as a curiosity, but as the very architecture of quantum matter. When many particles interact, their entanglement patterns define the phase they occupy, the way their collective behaviour emerges. It is as if entanglement were the blueprint, the hidden design that determines whether matter will flow like a liquid, stand firm like a crystal, or shift into one of those exotic moods we visited before. And in some of the newest experiments, researchers have noticed that entanglement itself can undergo transitions, like ice melting into water or water boiling into steam. These are called quantum information phase transitions, and they depend on a delicate balance between entanglement and observation. To imagine this balance, picture a tray of ice cubes on a warm day. Left undisturbed, they slowly melt, holding their crystalline patterns until the heat overwhelms them. But imagine if someone were to poke them constantly, nudging and disturbing their structure. The cubes would dissolve faster, unable to maintain their order. In quantum systems, too much observation has a similar effect. The act of measuring particles breaks their entanglement, collapsing the delicate web into simpler, less connected states. Like ice cubes vanishing under too many touches, the harmony dissolves when we press too hard. This does not mean that measurement is bad. It is, after all, the only way we learn. But it means that knowledge comes with a cost. To observe is to participate, and participation can fray the invisible threads. In everyday life, we feel something similar. A secret shared between friends holds a special power, but if retold too often, if examined under too many eyes, the intimacy fades. Entanglement thrives in privacy, in quiet connection, in the space where things are allowed to be without constant interference. The discovery that observation can melt entanglement has profound implications. It suggests that quantum systems live at the edge of a paradox. They need to be entangled to exhibit their strange powers, yet they need to be measured for us to use them. Too much observation, and the magic collapses. Too little, and the system remains silent, a treasure hidden in the dark. Technology built on quantum rules must therefore walk this tightrope, balancing between knowing and letting be. In this sense, entanglement becomes not just a physical glue, but also a metaphorical teacher. It reminds us that relationships flourish when given room to breathe. Push too hard, demand too much clarity, and the bond weakens. Allow space, allow trust, and the bond deepens. The same holds for quantum particles and for human hearts. But there is also resilience in this web. Some systems form what physicists call entanglement phases, where the connections are so deeply woven that even disturbances cannot easily unravel them. These systems behave almost like topological knots, where the pattern itself, rather than the specific threads, guarantees stability. Imagine braiding a rope so tightly that cutting one strand does not undo the whole. Such entangled phases could form the foundation of robust quantum computers and sensors, resistant to noise and error. They are not just delicate whispers, they are chords strong enough to carry songs across time. It is astonishing to realise that matter can depend so profoundly on relationships. We are used to thinking of particles as things, like marbles bouncing in a box. But the modern view tells us that what truly matters is not the marbles, but the patterns of entanglement among them. The identity of the whole cannot be reduced to its parts. It is the glue of relationship that gives birth to stability, to coherence, to resilience. Perhaps you have felt something like this in your own life. A group of people working together, each with their quirks and limits, but somehow forming a harmony greater than any individual effort. A family, a team, a community. Its strength lies not in the individuals alone, but in the invisible ties that connect them. Entanglement is the universe's way of doing the same, weaving particles into patterns that sing beyond the reach of solitude. So tonight, as you reflect on the quietness around you, think of the entangled webs humming beneath the surface. Think of electrons not as solitary wanderers, but as partners bound across space, their fates entwined. Think of the invisible glue that holds matter in forms stranger and stronger than we could have guessed. And think of the delicate balance, how knowing too much can melt the ice, while trust and space allow patterns to endure. The quantum world is not built from bricks, but from threads, and those threads are not fixed in place. They shimmer, they stretch, they respond to our gaze. Too much light and they dissolve, too little and they remain unseen. But in the balance, in the gentle act of looking without grasping too tightly, we find the possibility of new matter, new machines, and perhaps even new ways of being. Entanglement is not just a curiosity tucked into physics textbooks. It is the quiet glue that makes the world whole. If you have ever struck a match in the dark, you know the fleeting beauty of a spark. It flares, glows for a moment, and then fades, leaving only smoke and the memory of a light. For much of the early study of quantum matter, the discoveries felt like sparks, brief glimpses of strange phases, flashes of coherence in laboratories chilled to near absolute zero, phenomena so delicate that they vanished as quickly as they appeared. But over time, those sparks have been coaxed into longer flames. What began as fragile curiosities are slowly becoming solid systems, durable enough to be studied, harnessed, and perhaps someday woven into the fabric of our daily lives. One of the most promising transformations has come in the realm of superconductors. At ordinary temperatures, electrical wires behave like crowded streets. Electrons jostle, bump into atoms, and lose energy as heat. That is why your laptop warms your hands, why power lines hum and waste electricity along the way. But in superconductors, cooled and coaxed into special states, electrons stop behaving like individuals. They form pairs and flow as one, sliding through the material without resistance, without waste. It is as if the crowded street suddenly transformed into a wide river, where all the travellers glide effortlessly in the same direction. Superconductors were first discovered early in the 20th century, and at first they seemed impractical, requiring frigid temperatures to exist. But new families of materials, some working at much higher temperatures than before, have shown that this once fragile phenomenon might one day be part of everyday technology. Imagine cities powered by wires that whisper instead of burn, where electricity flows without loss, where the hum of waste heat is replaced by the silence of perfect efficiency. The dream is still distant, but it glows more brightly each year. Another transformation is happening in electronics built on quantum principles. The strange phases we explored, exciton condensates, Quantum liquid crystals, entangled webs, may lead to devices that are not brittle but self-sustaining, able to resist the noise and radiation that would normally disrupt them. In space, where cosmic rays batter circuits, such resilience could be the difference between failure and endurance. Here on Earth, it could mean phones and computers that do not overheat, sensors that last longer than their designers ever expected, networks that heal themselves like living tissues. To imagine this, think of a garden in spring. Some flowers wither quickly in the wind, their petals too delicate to endure, but others bend, sway, and continue to bloom, resilient not because they are rigid, but because they are flexible. Quantum matter, in its exotic moods, seems to hold this same quality. It is not brittle solidity that gives it strength, but harmony, the way electrons move together, sustaining each other like dancers who never fall out of step. Sensors are another place where fleeting sparks are becoming solid systems. Ordinary sensors measure the world by mechanical or electronic means. A thermometer expands mercury, a microphone vibrates a membrane. Quantum sensors, by contrast, lean on entanglement and superposition, letting particles themselves act as exquisitely sensitive instruments. Already, they have been used to detect minuscule changes in gravity, to map underground structures, to measure time with such precision that two clocks on different floors of a building tick at slightly different rates. In the future, these quiet instruments may track earthquakes before they are felt, follow the faint tremors of gravitational waves, or even listen in on the delicate rhythms of the human brain. It is striking to realize that these possibilities began as fragile glimpses in cold laboratories, a condensate lasting milliseconds, a pattern visible only under exacting light, a measurement so subtle it seemed impossible, and yet with patience those fleeting sparks are lengthening into steady flames, into systems that might one day be rugged enough for the messiness of the world. Science often moves this way, from whispers to words, from words to songs, from songs to symphonies that echo far beyond their first rehearsal. There is poetry in the idea of matter teaching us endurance. The quantum world is fragile when forced, but strong when allowed to harmonize. Our technologies too may learn to stop fighting noise and instead weave it into resilience, to stop burning energy and instead flow without loss, to stop breaking under stress and instead bend with it. In this, quantum matter offers not only new machines but new metaphors, that strength is not resistance alone, but coherence, and that beauty lies not only in sparks, but in the steady glow that follows. So tonight, as you picture the quiet streets of a city, or the soft hum of wires in your home, imagine them transformed. Imagine electricity flowing without waste, computers whispering instead of heating, sensors listening to the Earth's heartbeat. Imagine a world where the sparks of strange physics have grown into solid systems, reliable and enduring. We are not there yet, but the path is lit, and the quantum realm has already shown us that what begins as fragile can become resilient, and that what begins as fleeting can become part of the everyday. When we think of the quantum realm, we usually imagine it as hidden beneath scales too small to see, tucked away in the shadows of atoms and photons. It is a place of whispers, not shouts, of subtleties only mathematics can trace. Yet in the last few decades, scientists have begun to coax quantum effects into systems large enough to almost glimpse with the unaided eye. The boundary between invisible and visible has grown softer, as though the quantum world is not locked behind a wall but lapping gently at the edges of our everyday size. One of the most poetic examples comes from tiny mechanical resonators. These are objects built from silicon beams as thin as a human hair, or from aluminum membranes stretched like drumheads. Ordinarily, such devices vibrate in predictable ways. Pluck them with energy, and they ring like miniature tuning forks. But when cooled to near absolute zero and manipulated with delicate light or microwave signals, these resonators can enter quantum states. They can vibrate and not vibrate at the same time, holding their motion in superposition just as an electron can hover in two places at once. It is astonishing to realise that trillions of atoms stitched together in these structures can collectively display quantum strangeness. We're no longer talking about a lone photon or electron hidden in a chamber, but about systems large enough that you might in principle catch a glimmer of them through a microscope. They are not quite visible in the way a candle flame is visible, but they are close. So close that it feels as if the quantum realm is reaching out, brushing fingertips with our macroscopic world. To imagine this, think of a drum in a quiet room. If you tap it, the skin vibrates, sound waves travel, and your ears pick up the beat. Now imagine a drum so delicate that it is cooled to the brink of stillness, stripped of nearly all motion by refrigeration to temperatures colder than interstellar space. At that edge, when the drum is almost perfectly quiet, physicists can whisper to it with lasers or microwaves, coaxing it into superpositions. The drumhead then exists in two states at once, beating and not beating, a paradox you cannot hear with your ears, but one that shows up in the correlations of its signals. This is more than a curiosity. It demonstrates that the boundary between quantum and classical is not sharp, but porous. Our everyday world, with its tables and clocks and cups of tea, is built from quantum pieces. Normally their strangeness washes out, averaged over billions of interactions until certainty emerges. But under special conditions, scientists can keep the strangeness alive, preserving coherence long enough for larger systems to hum with quantum ambiguity. It is as though you took the mist of quantum uncertainty and condensed it into a sculpture you could almost see. There is a dreamlike quality to this work. Imagine standing in twilight, when the world is neither fully day nor fully night. Shadows lengthen, outlines blur, and familiar things look unfamiliar. These experiments live in that twilight between the small and the large, between invisible possibility and visible presence. The resonators are not part of ordinary experience, but they hint that quantum mechanics is not confined to realms beyond our senses. It is here, in objects big enough to hold in thought if not in hand. What is gained by creating these entangled macroscopic systems? Beyond the sheer wonder, they offer tools. Entangled resonators can act as ultra-sensitive detectors, picking up forces so faint they would normally vanish into noise. They can reveal how quantum coherence survives, how it fails, and where the tipping point between possibility and actuality lies. They let us test the limits of the theory itself. How far can superposition stretch? How large can entanglement grow before the classical world insists on clarity? These questions carry a quiet weight. If quantum behaviour can survive in resonators with trillions of atoms, perhaps it could be coaxed into even larger systems, challenging our intuition about what belongs to dreams and what belongs to waking life. Already, researchers have entangled vibrating drumheads across distances, showing that not only can one macroscopic object exist in superposition, but two can share that strangeness together, as if two bells on opposite ends of a cathedral rang in perfect but uncertain harmony. To soften this into everyday imagery, picture two pendulums hanging side by side. In ordinary life, you can set them swinging, and they might synchronize for a while, but their paths are clear, predictable. In the quantum laboratory, however, it is as though those pendulums share a hidden rhythm, swinging together in states not yet decided, bound by invisible threads of correlation. The effect is fragile, yes, but unmistakable. There is also something human in this exploration. We often wonder where the line lies between the abstract and the tangible, between the realm of thought and the realm of action. These experiments remind us that the line may not be as firm as we imagine. Reality seems comfortable existing in twilight, holding contradictions together until pressed to choose. And perhaps that is why we find such poetry in the idea of a drumhead that beats and does not beat. a breath of atoms that both stirs and rests. It resonates with our own experiences of uncertainty, our own moments of being half awake, half dreaming, suspended between choices. So tonight, as you listen to this story in the quiet, think of the almost visible quantum experiments humming in their laboratories. Think of drums stretched, thinner than hair, cooled to silence, nudged into paradox by careful hands. They are tiny, yet not too tiny, fragile, yet not invisible, a bridge between scales. They remind us that the strange is not locked away in hidden vaults of physics, but is slowly stepping out into the light, not to overwhelm but to whisper, not to dazzle but to linger, like twilight on the edge of day. When you walk into an old library, you might notice the silence is not empty but full. The faint rustle of pages, the creak of wood beneath footsteps, the whisper of air shifting through tall windows, all of it becomes audible only because you're quiet enough to hear. Quantum technologies feel much the same. They are not tools that roar with engines or dazzle with sparks. They are instruments of silence, sensitive enough to notice the whispers of the universe that ordinary tools would miss. Take quantum sensors, for example. At heart, they rely on the same principles we have already wandered through: superposition, entanglement, uncertainty. Instead of resisting these features, sensors embrace them, turning fragility into sharpness. Because quantum states are so delicate, they react to the slightest disturbance, and that reaction can be measured. An atom in superposition can serve as a clock so precise it feels the pull of gravity differently at the height of your knees than at the top of your head. Entangled particles can detect tiny shifts in fields or forces, their shared state broken if the environment so much as breathes on them. Already, quantum sensors are being used to measure gravity in ways once thought impossible. Imagine walking across a field with a quantum gravimeter, able to detect underground rivers or hidden tunnels by sensing the smallest variations in the pull of Earth. Imagine a network of such sensors spread across continents, listening to the subtle groans of tectonic plates, warning of earthquakes before they strike. These instruments do not shout, they listen. They reveal a world of quiet patterns beneath the noise of daily life. Other sensors lean on similar delicacy to measure time. Quantum clocks, operating with atoms that oscillate in steady rhythms, can keep time so precisely that they detect the stretching of seconds under gravity itself. Two clocks set only a few feet apart will drift, one ticking more slowly than the other, simply because one is closer to Earth's centre. In a sense, these clocks are listening to the warping of space-time, registering the gentle sag of the universe around massive bodies. For navigation, communication and science, such precision is transformative. For the imagination, it is humbling. But perhaps the most evocative tool born from these explorations is the quantum network, a web of entangled particles linking distant places. In ordinary communication, signals can be intercepted, copied, and overheard. In quantum communication, entanglement makes eavesdropping impossible. Any attempt to observe the particles changes their state, announcing intrusion immediately. Keys made this way are not locked with steel but with uncertainty itself, guarded by the laws of physics. In a future of tangled digital threats, such unbreakable security feels like a thread of calm. And these threads are not only secure, they are delicate. Entangled photons travelling through fibres or satellites are fragile travellers, undone by noise, by interference, by careless handling. Yet when carefully guided, they weave networks of breathtaking subtlety, a spider silk spun across the sky. Already, experiments have linked cities with quantum communication channels, and satellites have stretched these links across continents. One day, perhaps, a global quantum web will exist, an invisible net of light tying together oceans and mountains, carrying not just information but trust. To think of it in everyday terms, imagine a web of lanterns strung across a valley at night. Each lantern flickers, fragile against the wind, but together they mark a path, a network of light stronger than any single flame. That is how entangled photons behave. Alone, they are vulnerable, but woven into a net, they form something enduring. The image of spider silk returns here because it captures the paradox so well. A silk thread is almost weightless, invisible in sunlight, and yet ounce for ounce it can be stronger than steel. Quantum tools too are nearly invisible, their power hidden in fragility, their strength hidden in silence. They will not dominate the senses like roaring engines or towering machines. They will slip quietly into our world, reshaping it without spectacle, like threads woven into fabric so fine you do not see the weave until you step back. There is a softness to this vision. Imagine cities guided not by brute circuits that overheat and fail, but by networks of light and coherence. Imagine medical devices that use quantum sensors to read the faintest signals of the brain, not invasively, but by listening. Imagine explorers travelling through space with instruments that whisper of gravitational currents, long before eyes can see. None of this arrives with explosions or noise. It arrives like dawn, quiet, inevitable, spreading light. In all of this, what is most striking is how the strangeness of quantum rules, superposition, entanglement, uncertainty becomes useful. What seemed at first like flaws, like contradictions, become advantages. Fragility becomes sensitivity. Uncertainty becomes protection. Entanglement becomes connection. The very qualities that once unsettled us are now turning into instruments of resilience. So tonight, as you imagine the stillness of spider silk in morning dew, think of the invisible technologies slowly weaving themselves into the world. They are not here to dazzle you into wakefulness, but to remind you that silence can be powerful, that fragility can be strength, and that even the strangest rules of the universe can be turned into tools. The quantum world does not shout, but it leaves gifts, as delicate as silk, as unbreakable as trust. When we hear the word vacuum, the mind often pictures emptiness, a void without air, without dust, without sound. It seems like the ultimate quiet, a space stripped bare of everything. But the quantum realm teaches us that emptiness is never truly empty. Even the quietest vacuum, cooled and isolated, hums with restless energy. What appears to be silence is instead a hidden orchestra, playing notes too faint for ordinary ears. This idea that nothing is never really nothing comes from the notion of quantum fluctuations. In quantum mechanics, particles are never still. They are always uncertain, always trembling between possibilities. Even when you remove all matter and radiation, the vacuum still stirs with the brief appearance of particle-antiparticle pairs, popping into existence and vanishing almost immediately. They are not permanent residents, more like guests who step in, glance around and leave before the lights are fully on. Yet their presence is measurable, their influence real. The Casimir effect is one of the clearest ways to glimpse this restless emptiness. Imagine placing two perfectly smooth metal plates very close together, just nanometers apart. According to classical intuition, nothing should happen. They are simply sitting in empty space. But experiments show that the plates are pushed together by a tiny force. Why? Because the vacuum between them cannot hold all the same quantum fluctuations as the space outside. Certain modes of vibration are excluded by the narrow gap. The result is an imbalance with more pressure outside than within, nudging the plates toward each other. It is as if emptiness itself had weight, as if silence itself pressed its hands upon the plates. To picture it gently, think of a quiet room where some notes of music cannot fit. Outside the room, the full symphony plays. Inside, only a few notes echo. The imbalance nudges the walls inward, reminding us that silence is not absence, but a kind of filtered fullness. This restlessness of the vacuum may sound abstract, yet it has cosmic implications. The energy of empty space, what physicists sometimes call zero-point energy, is thought to drive the accelerated expansion of the universe. Galaxies are rushing away from one another faster and faster, as though the fabric of space itself were stretching. The simplest explanation is that even the vacuum carries energy, and this energy acts like a pressure pushing space apart. If that is true, then the largest force shaping the destiny of the cosmos comes not from stars or planets or black holes, but from the hum of emptiness itself. There is a paradoxical beauty here. Emptiness, which we associate with stillness, becomes the source of motion. Silence, which we imagine as absence, becomes a hidden song that drives galaxies apart. It is as if the universe carries within it a restless heart, beating even in the spaces between things. And though we cannot scoop vacuum energy into buckets or use it to power lamps in any practical way, the idea lingers in science fiction and daydreams. What if we could? What if the energy of nothing could become a resource, an endless tide upon which to sail? Even if such dreams remain distant, the mere existence of vacuum energy reminds us that our assumptions about nothingness are incomplete. What we call empty is, in truth, a stage alive with subtle players. Perhaps you have felt something like this in your own life. A pause in conversation that feels full of meaning, though no words are spoken. A quiet night where the silence seems to hum with possibility. A moment of stillness before sleep, when the mind is empty of thought yet buzzing with half-formed images. Emptiness is rarely truly empty. It is usually a canvas for what comes next, a fertile ground waiting for seeds. The vacuum of physics feels similar, a restless emptiness, fertile with fluctuations, waiting for the next act of the universe. So when you hear the word nothing, pause before imagining it as absence. In the quantum world, nothing is always something, a jitter, a hum, a pressure that shapes the largest patterns of space and time. Between galaxies, in the silent stretches of interstellar void, the restless empty continues, pushing the cosmos outward, whispering energy even where no matter resides. It is not silence, but the quiet music that underlies all songs, a rhythm so deep that we usually forget it is there. And tonight, as you rest in your own quiet space, think of the vacuum not as an absence but as a companion. Around you, between the walls and within the atoms, fluctuations stir, brief sparks of being rising and fading. The silence that surrounds you is alive, not with noise but with the hum of potential. You're never truly in emptiness. You're always embraced by the restless empty, the hidden fullness of the quantum stage. Time is something we are so sure we know. We wake to it each morning when alarms sing. We measure it in the hours of work and the minutes of waiting. We drift through it as we fall asleep. Yet when the quantum world touches time, it slips away from certainty, bending into questions that feel more like riddles than answers. In this realm, time does not always march in a steady line. Sometimes it seems to hesitate, sometimes to blur, and in certain experiments it even feels as though the future can lean back and influence the past. One of the most curious demonstrations of this comes from John Wheeler's delayed choice experiment. It builds on the double-slit story we visited earlier, where photons act like waves when unobserved, but like particles when measured. Wheeler asked, "What happens if you wait until after the photon has already passed the slits to decide whether to measure its path? Logic suggests the photon's behaviour should already be decided, yet the results show otherwise. If you choose to measure the path later, the photon's earlier behaviour aligns as though it had always been a particle. If you choose not to measure, the photon's earlier behaviour aligns with a wave. The present decision seems to ripple backward, finalising what the photon did in the past. It is tempting to imagine this as rewriting history, like editing a book after it has been published, but that is not quite right. A better way to see it is that the story was never fully written until the end. The photon carried with it a haze of possibilities, and only when the entire experiment concluded was the narrative sealed. The past was not erased, it was completed, filled in with ink only after the last page was turned. This hints at an unsettling idea, that time in the quantum world may not be a strict arrow from past to present to future, but a more flexible tapestry, woven from threads that can stretch backward and forward depending on how the loom is used. Retrocausality, as some call it, is not about sending messages into the past or changing what already happened in everyday life. It is about recognizing that in the quantum play the script is written only once the curtain falls, and until then, past and present remain open to interpretation. There is another way quantum mechanics reshapes time, and it comes not from paradoxical experiments but from precision. Quantum clocks, built on atoms oscillating at steady, nearly perfect frequencies, can measure time with such accuracy that they detect the bending of time itself under gravity. According to Einstein's relativity, time runs more slowly in stronger gravitational fields. Place one clock at the bottom of a mountain and another at the summit, and the one below ticks ever so slightly more slowly. For decades, this was a prediction confirmed only at large scales, like satellites compared to Earth. But with quantum clocks, the difference can be measured across a single building, even across the height of a human. Time, it turns out, is not uniform even across your body. Your feet are aging just a tiny bit more slowly than your head. To imagine this, picture two metronomes clicking in unison on a table. Lift one by only a few centimetres, and it begins to slip ahead, each tick drifting from its partner. Nothing seems different, yet the rhythm has changed, pulled apart by the invisible gradient of time. The universe does not grant us a single universal beat. It lets every point in space keep its own tempo, all slightly different, all woven into the grand symphony of relativity. The quantum clock is not just a marvel of precision, but a reminder that time itself may be emergent, not absolute. Some physicists speculate that time could arise from entanglement, from correlations between particles, rather than being a fundamental background. If so, then what we call time might be more like a measure of change, a record of relationship shifting, rather than a river flowing on its own. In this view, clocks do not count an external stream, they help create it, shaping time as much as measuring it. For us, these ideas invite reflection. We live by schedules, alarms, and calendars, but beneath them lies a world where the arrow of time is not so simple. At small scales, the past waits for the present to decide. At human scales, time bends under gravity's hand, ticking differently at each height. And perhaps, at the deepest scales, time is not an independent thing at all, but a rhythm born from relationships, an emergent hum like the resonance of strings in a violin. So tonight, as you feel the moments passing, imagine them not as seconds slipping from a universal clock, but as pages written only when you turn them, as rhythms that differ depending on where you stand, as stories completed only when the curtain falls. The quantum world reminds us that time is not just something we measure. It is something we participate in, something we shape with every observation, every relationship, every breath. And in that sense, to rest is not to waste time, but to enter into it differently, to let the rhythm soften, to let the narrative pause before choosing its next line. Time in quantum hands is not rigid but pliant, not dictatorial but conversational. It listens as much as it tells. And as you drift towards sleep, you're not stepping outside of time but into another of its moods, a gentler tempo, a different chapter in the same unfolding book. There is an old saying that you cannot get something from nothing. It sounds sensible, like a rule carved into the foundation of common sense. If the cupboard is empty, you cannot bake a cake. If your wallet is bare, you cannot buy bread. But in the quantum realm, even this sturdy saying begins to waver. For there, Nothing is never truly nothing, and from the restless emptiness tiny loans of energy appear, borrowed for a moment before being paid back with such speed that the books of physics remain balanced. This strange generosity of the vacuum comes from the jitter of quantum fluctuations which we touched upon earlier. Virtual particles, brief as sighs, emerge and vanish. Their lifespans are so fleeting that they leave no permanent mark, yet in certain clever experiments their presence can be nudged, even manipulated. Scientists have learned how to relocate tiny amounts of this vacuum energy, coaxing the emptiness itself to shift its balance, as though silence could be persuaded to hum in a slightly different key. One way this appears is in experiments with squeezed light, where the fluctuations of the vacuum are shaped to reduce uncertainty in one property at the cost of increasing it in another. It is like borrowing from one pocket to fill another, keeping the sum the same but rearranging the weight. These manipulations let detectors, such as those listening for gravitational waves, sharpen their ears, reducing noise from the quantum jitter of light. In this way, nothing is not only restless but useful, lending its energy to improve our ability to listen to the universe. The idea of vacuum energy naturally invites daydreams. Could it be tapped like a cosmic reservoir, fueling engines, lighting cities, carrying ships to the stars? Science fiction loves this possibility, imagining reactors powered by the energy of emptiness itself. Reality is gentler. The amounts of energy we can manipulate are minuscule, tiny nudges rather than roaring rivers. The laws of physics insist that any borrowing must be repaid almost instantly, keeping the cosmic books in order. The vacuum gives, but it also takes back. And yet, the thought lingers. What if the largest force in the universe, the energy of the vacuum driving the accelerated expansion of space, is a reminder that emptiness itself can be the greatest something of all? Galaxies are rushing apart not because of stars or matter, but because the vacuum itself carries a push. Even if we never build reactors from nothing, we're already living in a cosmos shaped by it. Our very future as a universe, the rate at which stars drift apart, the horizon beyond which light can never return, all of it depends on this quiet pressure of emptiness. To imagine it, think of a balloon inflating, not because someone blows air inside, but because the rubber itself insists on stretching. Space behaves in this self-stretching way, expanding not from an external cause, but from its own vacuum energy. It is a universe borrowing from nothing and paying it back with expansion, a restless balance carried out on scales we can scarcely fathom. There is poetry in the thought that the largest forces come from what we would have once called nothing. It suggests that absence is an illusion, that every silence hums, every pause resonates, every void carries seeds of becoming. In daily life, too, nothing often hides something. A quiet room may feel empty until you notice the sound of your own breathing. A pause in conversation may feel like silence until you sense the unspoken words that hover between friends. A night sky may look like darkness until your eyes adjust and you see it sprinkled with stars. So perhaps it is fitting that physics itself reveals a similar lesson, that even the void is full, that nothing is not a barren desert but a restless sea. We cannot scoop its waters into buckets or power our lamps with it, but we can let it guide us, shape our instruments, and remind us that potential exists even in the most unlikely places. And maybe this is why the idea of borrowing from nothing feels comforting rather than unsettling. It tells us that the world is not as austere as it appears. Beneath every silence lies a hum. Beneath every stillness lies motion. Beneath every absence lies possibility. The vacuum in all its strangeness is not an empty stage waiting for actors, but an actor itself, moving the play forward with subtle gestures. So tonight, as you lie in the stillness of your own room, imagine that the quiet around you is not empty but alive with fluctuations too small to feel. Imagine that silence is not hollow but full, not barren but fertile. The emptiness you sense is not absence, but presence in disguise. And if you feel that you too are sometimes empty, remember that emptiness can carry its own fullness, its own hum of possibility, waiting only for the right moment to unfold. When you stand in front of a shelf of books, you cannot read them all at once. You choose one, you open its pages, and you walk the path of its story. The other books remain closed, their tales untouched. Ordinary computers work much the same way. Each bit of information is either a 0 or a 1, open or closed, like the single book you hold in your hand. To solve a problem, the computer must move through one sequence of choices at a time, like a diligent reader moving page by page. Quantum computers, by contrast, are like a library where the shelves seem to read themselves all at once. Their basic units, called qubits, are not confined to being 0 or 1. They can exist in superpositions, a blend of both possibilities. When many qubits are entangled together, they can hold an orchestra of states simultaneously. Instead of one book open, the library whispers every story, every combination, before choosing which to reveal. To picture this without mathematics, imagine tossing a coin. In the ordinary world, the coin is either heads or tails when it lands. In the quantum world, the coin can spin in a superposition of both, heads and tails together, until someone looks. Now imagine not one coin, but dozens, each linked with the others, their spins coordinated in subtle ways. The number of possible patterns grows not step by step, but exponentially. A few qubits can explore landscapes of possibility so vast that classical computers, even the most powerful, cannot follow. This is why quantum computing has captured such imagination. It is not just a faster engine, it is a different mode of thought, a way of letting problems blossom into many paths at once. For certain tasks, simulating molecules, searching vast data sets, optimizing complex systems, this ability could transform what is possible. Problems that would take classical computers longer than the age of the universe to solve might yield to quantum algorithms in a reasonable time, provided we can build machines stable enough to hold their delicate states. But these machines are not easy to make. Qubits are fragile, their superpositions easily destroyed by noise, heat, or stray interactions with the environment. Keeping them coherent is like trying to hear a whisper in a crowded marketplace. Researchers cool them to near absolute zero, shield them with layers of protection, and correct their errors with clever techniques. Progress is slow, but steady. Already, prototype quantum processors exist, with dozens or even hundreds of qubits. They are not yet powerful enough to surpass classical giants in general tasks, but they are learning to hum, to sing their strange harmonies for brief moments. Think of it like raising a choir of children. At first the voices waver, the timing slips, the harmony dissolves. But with patience, with guidance, the voices align. The challenge of quantum computing is much the same. Teaching fragile qubits to hold their tune, to sustain their coherence long enough to complete a symphony of calculation. There is something dreamlike in imagining a computer that explores possibilities not sequentially but simultaneously. It is almost like daydreaming, where the mind wanders down many roads at once. What if I had gone there? What if I had said this? What if the future bends that way? Quantum computers turn this wandering into structured exploration, weighing countless outcomes before collapsing into one answer. They are machines that daydream, but with discipline. And yet, it is important to remain humble. Quantum computers will not replace every laptop or phone. For most tasks, writing letters, browsing the web, streaming music, classical bits remain perfectly efficient. Quantum machines will shine in specialized realms where the richness of superposition offers shortcuts no ordinary process can match. They may simulate proteins for new medicines, design novel materials with properties we cannot yet imagine, optimize traffic flows in cities, or crack mathematical problems that lie beyond current reach. Their gift is not speed alone, but depth, the ability to swim in seas of possibility. In this sense, The many worlds of a calculation are not about parallel universes, though the metaphor is tempting. They are about parallel possibilities, explored in a single breath of computation, then distilled into one outcome. The machine does not create alternate realities. It samples them as shadows, then gathers the most useful echoes into the world we inhabit. Perhaps this is why the thought of quantum computing feels both exciting and oddly human. We too live in superposition much of the time. Before a decision, we are many selves, imagining different futures, different choices. Only when we act do we collapse into one story, leaving the others behind. A quantum computer formalizes this human experience, turning it into hardware and algorithm, amplifying the natural ambiguity of choice into a tool. So tonight, as you think of the world's quiet technologies humming in their circuits, imagine a different kind of hum. Qubits whispering across superconducting loops, ions dancing in traps, photons entangling across fibers. They are fragile, yes, but also promising. They are the many worlds of calculation, the dream of a library that reads itself, the whisper of a machine that daydreams in order to solve. There is a certain comfort in secrets, a whispered thought between friends, a letter tucked away in a drawer, a look across a room that means something only to the one who knows. We rely on secrecy in larger ways too. Bank accounts, medical records, private conversations. So much of our daily life depends on trust that what is meant for us stays ours. In the ordinary world, secrecy is guarded with locks and keys, with codes that take great effort to break. But in the quantum world, secrecy is guarded by the laws of physics themselves, as though the universe has taken it upon itself to keep certain things safe. This is the promise of quantum cryptography, which uses entanglement and the delicacy of measurement to secure communication. Imagine two people, far apart, sharing a stream of entangled photons. Each photon pair carries correlated properties. When one person measures their photon, the other, even across great distance, sees a matching result. The pair can use these shared outcomes to form a key, a string of numbers that unlocks messages. The magic lies in the fact that if anyone tries to eavesdrop, their observation disturbs the photons, breaking the correlations. The intrusion is instantly obvious. Unlike ordinary codes, which can be cracked with enough effort, quantum keys announce when they have been tampered with. It is as if every whisper came with a built-in alarm that rings the moment an outsider leans too close. To soften this image, think of two friends playing a private game of dice across a curtain. Each roll is hidden, but when one calls out the number, the other always finds theirs matches. If a stranger peeks through the curtain, the dice shift, the game stumbles, and the friends know at once that the bond has been disturbed. In this way, quantum cryptography makes secrecy less about clever locks and more about fragile trust. The universe itself becomes the lock, and it does not permit quiet tampering. Already, quantum cryptography has moved from theory to practice. Satellite experiments such as those with the Chinese satellite Messias have demonstrated secure links over thousands of kilometers, distributing entangled photons between ground stations. Though still limited, these experiments suggest a future where communication networks might be stitched together with quantum keys, offering privacy that no spy or hacker can undo. It is not a fortress built of walls, but of transparency. If anyone tries to intrude, you simply see them. As comforting as this is, there is another gift the quantum world offers, one that feels stranger still: teleportation. When we hear the word, we imagine science fiction. People dissolving in one place and reappearing in another, ships beaming passengers across space. Quantum teleportation is more modest and more profound. It does not move matter, but it moves information, the very state of a particle, from one place to another, using entanglement as the bridge. To understand it gently, imagine you have a delicate pattern embroidered on a cloth. You cannot send the cloth itself across the ocean, but you can send a description, so exact that someone far away can stitch an identical pattern onto a new cloth. In quantum teleportation, the pattern is the state of a particle, and the entanglement shared between sender and receiver provides the fabric upon which the pattern is rewritten. The original state disappears where it was and reappears in the new place. The particle itself does not travel, but its identity, its essence, does. This process has been demonstrated with photons, with atoms, even with small groups of particles. The distances are growing, from laboratories to satellites, and though we are far from teleporting people or even large objects, the principle has been proven again and again. It is not a magic trick, but a disciplined choreography, entanglement, measurement, and reconstruction working together like dancers passing a rhythm across a stage. What does it mean for us? At first, not much changes. Our bodies will not dissolve into beams of light. But in technology, teleportation may become a backbone of quantum networks, allowing quantum states to be transmitted securely and reliably across long distances. It is a way of extending entanglement, of stitching distant systems into a single fabric. Where cryptography offers secrecy, teleportation offers connection, turning the fragile whispers of quantum states into messages that can travel without being corrupted. There is something deeply human in both of these tools. One protects the privacy of our words, ensuring that what is meant for us stays ours. The other carries our messages across distance, ensuring that what we send arrives intact. Together they echo the ancient needs of communication, to keep what is private safe and to bridge what is far apart. The quantum world does not reinvent these needs. It simply offers a subtler, more delicate way to fulfill them. And perhaps there is a lesson hidden here as well. Cryptography reminds us that observation itself changes the story, that secrecy lives in the balance between sharing and protecting. Teleportation reminds us that identity can be carried not by the object but by the pattern, not by the body but by the state. Both are strange, both unsettling, and yet both are quietly reassuring. The universe, in its quantum depth, seems to offer us tools not of domination but of trust, not of spectacle but of subtlety. So tonight, as you listen in the stillness, imagine threads of entangled light stretching between cities, carrying secret keys that no one can steal. Imagine patterns of quantum states leaping from place to place, like whispers carried not on air but on the fabric of reality itself. These are not dreams of fiction alone. They are experiments already unfolding, sparks already catching. They are the quiet technologies of secrecy and connection, gifts of a universe that guards its whispers and carries them faithfully across the void. When we speak of intelligence, whether human or artificial, we usually imagine a process of choices, step by step, one possibility examined, one conclusion reached, one decision made. Even the most advanced classical algorithms are like diligent readers, moving through their calculations in a line, branching when necessary, but always confined to the rails of sequential logic. But in the quantum world, where possibilities do not politely wait their turn but mingle and overlap, there lies a different kind of thinking, one that whispers of intelligence built not from steps alone but from clouds of potential. The idea of quantum artificial intelligence is still young, a phrase more dream than blueprint. At its heart is the suggestion that quantum computers, with their qubits dancing in superposition and their webs of entanglement, could be used to simulate not just molecules or materials but minds of a sort. Algorithms capable of exploring countless options in parallel before settling on a course. Where classical AI struggles with the limits of linear paths, quantum AI would daydream in many directions at once. To imagine this, think of yourself standing before a crossroads at night, unsure which road to take. A classical machine would walk each road in turn, measuring their lengths, their obstacles, and then return to report. It is efficient but time-consuming. A quantum machine, in principle, could step onto every road at once, drift along their lengths, sense their outcomes, and then collapse back into one body, carrying the memory of them all. The choice would not be the product of trial and error, but of parallel experience. There is something dreamlike about this. It recalls the way the human mind sometimes works when left in reverie. You think of what might happen if you take a job or decline it, if you say yes to love or turn away, if you move to a new city or remain where you are. In a single breath, you hold several futures, tasting them before deciding which to pursue. Quantum AI, if it ever arrives, might formalize this drifting into possibility, turning it from metaphor into mechanism. Already, researchers sketch the outlines. Quantum machine learning algorithms are being designed to recognize patterns faster, to search through vast datasets with subtler efficiency, to optimize choices in fields as complex as logistics or finance. These early efforts are modest, running on small quantum processors prone to error, more prototypes than partners. But they hint at what might be possible if fragility is tamed and coherence sustained. A quantum-enhanced AI could be a tool for discovery, spotting solutions that classical systems would take eons to find. And yet there is caution here. Just as with all dreams of intelligence beyond our own, there is the risk of expecting too much or too soon. Quantum computers are fragile instruments, their whispers easily drowned by noise. Building AI upon them is like trying to sculpt mist into form. It may yield delicate shapes for a moment, but they vanish if pressed too hard. The path from speculation to reality is long, and for now the whispers of quantum AI remain mostly that, whispers. Still, there is value in whispers. They remind us of directions we might someday take, of horizons we have not yet reached. Even if quantum AI remains distant, the very idea reshapes how we think about intelligence. It suggests that thought need not be confined to sequential steps, that reasoning itself could be a cloud of possibilities narrowing into clarity. It suggests that creativity might come not only from following lines, but from hovering above them, holding many at once before choosing one. And perhaps it invites us to reflect on our own thinking. How often do we treat our decisions as fixed, as if the only way to know is to choose? How often do we forget that we too can drift in imagination, hold several options together, taste them lightly before collapsing into one? The quantum realm reminds us that ambiguity is not a flaw, but a stage of being, and that intelligence, human or artificial, may thrive in ambiguity rather than resist it. There is also a poetic symmetry in the idea of building intelligence upon entanglement. We too are creatures of entanglement. Our minds are shaped not in isolation, but in webs of relationship, language, culture, memory. If quantum AI ever takes form, it may not be a solitary thinker, but a networked one, its strength drawn from patterns of connection. It may remind us that intelligence is less about answers and more about relationships, less about certainty and more about coherence. So tonight, as you rest, imagine a machine not clanking with gears or humming with circuits, but whispering with probabilities. Imagine it drifting across possibilities like a dreamer half awake, considering paths in parallel, collapsing gently into one choice at the end. It is not here yet, but the whisper is enough. The whisper says that thought itself can be broader than we imagine, that the universe does not forbid such dreaming, and that perhaps in the quiet interplay of superposition and entanglement lies a new kind of intelligence waiting to emerge. When you step outside on a bright morning, you may notice how leaves seem to glow. Sunlight pours down in golden sheets, and the green surfaces around you shimmer with a quiet confidence, as though they know how to welcome light better than we ever could. For most of us, photosynthesis is something we learned about long ago in classrooms. Plants take in sunlight, water, and carbon dioxide, and they turn these into sugar, the fuel of life. But beneath that familiar story lies a quieter secret, one whispered not in biology textbooks, but in the language of quantum physics. Photosynthesis is not just a chemical trick, it is a quantum performance. When a photon of sunlight strikes a leaf, it excites an electron, raising it into motion like a spark leaping onto a pathway. The goal of that spark is to travel to the plant's reaction center, where its energy can be converted into chemical bonds stored as food. You might think this would be a straightforward journey, like water flowing down a pipe. But inside the leaf, the path is more like a tangled forest. Many routes wind through molecular mazes, and some are longer or more obstructed than others. If the energy moved like a classical traveller, it would wander aimlessly, wasting precious sunlight. Yet plants are astonishingly efficient. They capture and deliver energy with a success rate that far surpasses our best solar panels. How do they manage this? The answer seems to be quantum coherence. Instead of the energy choosing one path at random, it spreads like a wave across all paths at once, sampling every option simultaneously. The wave interferes with itself, cancelling out the longer, less efficient routes and reinforcing the quicker, straighter ones. In this way, the energy almost instantly finds the best path to the reaction centre. Imagine tossing a pebble into a pond and watching the ripples fan out. Now imagine that every ripple carries the energy of sunlight, exploring all directions at once. Some ripples overlap constructively, guiding the energy forward, while others cancel out, discarding wasted paths. The result is a choreography of waves that funnels the spark with astonishing speed and efficiency. The plant does not waste time guessing. It lets quantum rules do the work. Researchers discovered this by shining ultra-fast laser pulses into photosynthetic complexes and watching the patterns of energy. To their surprise, they found oscillations lasting far longer than expected, signatures of coherence, waves of probability holding together even in the warm, messy environment of a leaf. This was startling, because coherence is usually fragile, destroyed by heat or noise, yet plants seem to maintain it, protecting quantum effects long enough to harvest sunlight. There is something humbling in this discovery. For decades, we assumed that quantum strangeness belonged to cold laboratories, to atoms chilled and isolated. And yet here it was, thriving in the gentle warmth of leaves, in the everyday act of sunlight meeting chlorophyll. Nature had quietly mastered a trick that human technology still struggles to replicate. To soften the image, think of an orchestra playing outdoors. Normally gusts of wind or chatter from the crowd might disrupt the harmony. But in the photosynthetic orchestra, the musicians stay in sync, their notes weaving together despite the noise of the environment. The melody continues, clear and efficient, carried across the stage of the leaf. The implications extend beyond admiration. If we could learn to mimic this quantum coherence, our solar technologies could leap forward. Panels that now capture only a fraction of sunlight's gift might one day rival the efficiency of leaves, turning rooftops into green machines of their own. Scientists are already exploring designs inspired by photosynthesis, hoping to capture not just photons but the quantum choreography that makes their journey so efficient. But beyond technology, there is a softer lesson. The leaf reminds us that nature does not waste. It does not choose clumsily among paths. It embraces all paths at once, lets them overlap, and then lets interference guide the way. There is a wisdom in that. To consider many possibilities before deciding, to allow the world's patterns to sort themselves out rather than forcing a choice too soon. So the next time you sit beneath a tree and feel the shade upon your skin, imagine the quiet green machines above you. Each leaf is a laboratory more subtle than any we can build, taking in photons that left the sun 8 minutes ago, spreading their energy across a network of paths and funneling it into life. The process is silent, tireless, and older than history. Long before humans spoke of qubits and coherence, The leaves were practicing these arts, humming their quantum songs in the language of chlorophyll. And tonight, as you drift into rest, you might think of yourself as a little like those photons. Your thoughts wander down many paths, some longer, some shorter, some wasteful, some efficient. In dreams they overlap, they interfere, they guide you along strange routes. Only when you awaken do you find which path was taken. Like sunlight in a leaf, your journey is not wasted but woven, carried by a choreography deeper than choice, guided by the whisper of quantum rules that underlie even the green shimmer of morning light. Step outside on a spring morning, and you might hear a bird call sharp and clear, as though it carries the whole season in its voice. You might watch it lift into the air, wings catching sunlight, and feel a passing curiosity about how it knows where to go. Migration has always seemed almost magical. Tiny creatures crossing oceans and continents, finding their way to places they have never seen. For years we explained it with instincts, with stars and landmarks, with cues written into the earth itself. Yet deeper studies have uncovered something stranger, that birds may be navigating with the help of quantum mechanics, as though their eyes can see a map invisible to ours. The secret may lie in proteins inside their retinas, proteins that respond to light by creating entangled pairs of electrons. These pairs are exquisitely sensitive to magnetic fields. Depending on the orientation of Earth's field, the entangled spins shift, influencing chemical reactions in the bird's eye. The result may be a faint ghostly pattern, superimposed on their vision, a kind of overlay showing north and south. To us, the world is a wash of colours, but to birds, it may also shimmer with magnetic hues painted by entanglement itself. To picture it, imagine wearing a pair of glasses that tint the world differently depending on which way you face. Look north, and the colours shift toward blue, turn west, and they slide toward green. The glasses are not ordinary lenses, but sensors attuned to invisible forces. Birds may carry such glasses in their biology, not made of glass but of molecules, tuned by evolution to harness quantum rules. Smell, too, may involve quantum tricks. For a long time, scientists believed that scent was explained simply by shape. Odour molecules fit into receptors in our noses like keys into locks. But some puzzles refuse to fit. Certain molecules with nearly identical shapes smell entirely different. Others with different shapes smell oddly similar. A competing idea, called the vibrational theory of smell, suggests that receptors do not only test shapes but also listen to vibrations. When a molecule enters a receptor, electrons may tunnel through it if its vibrational frequency matches the right energy. This tunneling, a purely quantum effect, could help distinguish scents. Imagine striking a tuning fork and hearing its note. Now imagine sliding a bow across a violin string that resonates with that note. The vibration passes through, ringing true. In the nose, the vibration is not sound but molecular motion, and the bow is not a string but an electron tunnelling through. If the match is right, the passage succeeds, signalling scent. In this view, the nose is not just a cabinet of locks and keys, but an orchestra of vibrations, resonating with the molecules of the world. And then there are enzymes, those molecular machines that catalyse life's chemistry. Reactions that would take millions of years in plain water happen in seconds inside cells guided by enzymes. For decades, we explained this in terms of shape and proximity. Enzymes hold molecules close, align them, and lower barriers so reactions can proceed. Yet some reactions seem to occur faster than even this explanation allows. Evidence suggests that enzymes may also harness quantum tunneling, letting protons or electrons slip through energy barriers instead of climbing over them. To soften this image, think of a child facing a tall fence. Ordinarily, she must climb it, pulling herself over the top. But if she could somehow pass through a hidden gate in the fence, she would arrive instantly on the other side. Tunneling is that hidden gate. Enzymes may guide particles to such gates, letting life's chemistry leap forward with breathtaking efficiency. What is striking is how these quantum effects thrive in warm, noisy environments. For years, physicists assumed that coherence and tunneling were too fragile for biology. Yet, here they are, woven into senses and reactions that make life possible. It is as if nature has not only learned the rules, but plays them with artistry, weaving entanglement into migration, tunneling into scent, coherence into photosynthesis. The quantum realm is not confined to laboratories, it is alive in feathers, in noses, in cells. For us, this blurs the line between physics and biology, between the abstract and the everyday. The bird that glides overhead may be navigating with entangled electrons. The aroma of morning coffee may carry signatures of quantum tunneling. The very speed of the enzymes in your body, sustaining your breath and thought, may depend on particles slipping through barriers as though walls were illusions. There is a quiet poetry in realizing that our senses and our survival are tied to rules stranger than any we first imagined. It reminds us that life does not sit apart from the universe. It is one of the universe's own expressions, shaped by the same mysteries that govern light and atoms. To live is to be quantum, whether or not we notice. So tonight, as you rest, think of the bird winging its way under starlight, guided by invisible maps written in entanglement. Think of the faint aroma of tea drifting upward, carried not just by molecules but by tunneling electrons. Think of the enzymes in your cells, catalyzing life's chemistry at speeds unfathomable without quantum gates. You're surrounded by quantum hues, not just in laboratories but in the green of leaves, the scent of flowers, the flight of wings, and the pulse of your own blood. There is a special hush that falls when we turn the question inward, from the outside world of stars and particles to the inner world of thought. The quantum realm has already shown itself in plants, in birds, in scents, in the chemistry that animates our cells. But could it also whisper within the folds of the brain, in the rhythms of thought, in the texture of consciousness itself? Here, the ground grows uncertain. The science is tentative, the debates sharp, and the evidence fragile. Yet the very possibility invites us to linger, if only in imagination, at the edge of one of the most enduring mysteries, what it means to be aware. One of the most discussed ideas is the Auchoir theory, short for orchestrated objective reduction, proposed by physicist Roger Penrose and anesthesiologist Stuart Hamroff. They suggested that consciousness arises not merely from the firing of neurons, but from quantum processes within microtubules, tiny structural filaments that form the scaffolding of cells. In their view, quantum superpositions within microtubules could be orchestrated into coherent patterns, and when these patterns collapse, they give rise to moments of awareness. Each collapse would be like a flicker of light, a beat in the rhythm of consciousness. To soften this image, think of a cathedral filled with organ pipes. Air rushes through, producing a blend of notes. Normally the sound would be chaotic, but if someone orchestrates it, aligning the notes, the music becomes rich and resonant. The Auchoir theory suggests that the brain's microtubules may act like such pipes, orchestrating quantum states into the music of mind. It is a bold vision, weaving physics into the deepest folds of biology. Critics argue that the brain is too warm, too noisy for such delicate quantum effects to persist. Coherence, they say, collapses in femtoseconds under such conditions far too short to influence thought. Supporters counter that nature has already surprised us. Leaves and enzymes sustain quantum tricks in noisy environments, so perhaps the brain has its own protective strategies. The debate remains unresolved, poised between skepticism and possibility. Beyond Auchoir, there are other whispers of quantum links to mind. Some studies claim to find deviations in random number generators when groups of people focus their attention, as though intention itself could nudge chance. Others point to brainwave synchrony across individuals in shared experiences, suggesting a subtle resonance that goes beyond simple signals. These ideas remain controversial, their data fragile, their interpretations disputed, but they stir curiosity, hinting at connections that may not yet be understood. It is important here to step carefully. None of these ideas have reached consensus. They live in the borderlands between science and speculation, in the twilight where hypotheses wait for clearer evidence. And yet, there is value even in these borderlands. They remind us that consciousness, for all our progress in neuroscience, is still profoundly mysterious. We can trace neural circuits, measure brain activity, and even simulate aspects of thought. But the raw feel of awareness, the taste of tea, the sound of rain, the sense of being you, remains unexplained. To wonder whether quantum processes might play a role is not to claim certainty, but to admit wonder. Perhaps the real gift of these speculations is the way they invite us to imagine consciousness not as a fixed property, but as a rhythm, a flow. If Orch-Or is correct, awareness might not be a continuous stream, but a flicker of moments, stitched together so finely that we experience them as seamless. If coherence in the brain can survive long enough, thought itself might be a tapestry woven from quantum threads. And if our minds are in some sense entangled with one another, as the more adventurous theories suggest, then perhaps awareness is less private than we assume, more like a field we share than a fortress we inhabit. To give this a gentler shape, think of fireflies in a meadow. At first they blink randomly, each unaware of the others, but slowly in some places they begin to synchronize, their flashes aligning into waves of light. Consciousness may be something like this. Quantum flashes aligning into coherence, each moment of awareness linked to the next, each mind perhaps even resonating faintly with others. Whether the details of Orch-Or or similar theories survive scrutiny, the metaphor remains compelling. For us, what matters is not only the science, but the perspective it offers. To consider consciousness in quantum terms is to see awareness not as an isolated spark, but as part of the universe's ongoing play of uncertainty and collapse, of coherence and decoherence. It suggests that our thoughts are not exceptions to the laws of physics, but participants in them, woven from the same strangeness that shapes photons and electrons. So tonight as you rest, consider that your own awareness, the drifting of thoughts, the fading of wakefulness into dreams, might itself be a dance at the edge of certainty. Perhaps it is orchestrated by microtubules, perhaps by neurons alone, perhaps by processes we have not yet imagined. Whatever the case, the mystery of consciousness is not diminished by speculation. It is deepened. The fact that we can ask the question at all, that the universe has produced creatures who wonder about their own awareness, is itself a marvel. And if quantum mechanics whispers in the folds of that awareness, then perhaps our thoughts are not only about the universe, but part of its own self-reflection, a dream within a dream. When John Wheeler, the physicist who helped shape much of 20th century physics, was asked what the universe is made of, he gave a curious answer. Not atoms, not particles, not even energy. He said, "It from bit." By this he meant that every it, every object, every particle, every star, is at its foundation a manifestation of information, a bit that comes into being when a question is asked, when an observation is made. Reality in this view is not a stage already built, waiting for us to walk upon it. It is a play written as it is performed, with audience and actors entwined. This idea, sometimes called the participatory universe, flows naturally from the quantum experiments we have wandered through. The double slit shows us that photons behave like waves or particles depending on how we observe. The delayed choice experiments hint that the past itself is shaped by present decisions. The quantum Zeno effect demonstrates that scrutiny can hold systems in place. Again and again, the message whispers, observation matters. The universe is not indifferent to our questions. It answers in ways that depend on how the question is posed. To picture this more gently, Think of a storyteller improvising a tale for a circle of listeners. If the listeners lean in, eyes wide, the story grows in one direction. If they laugh at a certain detail, the storyteller takes another path. The story is not pre-written, but co-created, a dialogue between teller and audience. In Wheeler's vision, the universe is such a story, and we are not passive listeners but participants, helping to bring the plot into being with every observation we make. This does not mean that consciousness alone wills planets into existence, or that reality bends to our desires. It is subtler, quieter. The participatory principle says that the universe is incomplete without observers, that the act of measurement is part of its fabric, that the questions asked are as real as the answers given. In this sense, we are woven into the cosmos not as outsiders looking in, but as threads in the loom, part of the pattern as it unfolds. Some have taken this idea further, speculating that consciousness itself may be non-local, perhaps even field-like, connecting minds across distance. Others imagine that the universe requires life, in some form, to become real at all. These are bold conjectures, not settled truths, but they spring from the same recognition. The boundary between subject and object, between observer and observed, is not as firm as we once believed. There is a quiet humility in this. For centuries, we imagined ourselves as small, insignificant creatures on a tiny planet, gazing up at a vast cosmos that cared nothing for us. The participatory universe does not erase that humility. We are still tiny, still brief, but it adds a new layer. It suggests that our gaze is not meaningless, that our questions echo into the fabric of reality itself. To observe is to participate, and to participate is to belong. Perhaps you have felt something like this in your own life, a conversation that seemed to change depending on the attention you gave it, a piece of music that bloomed differently when you listened closely versus when it played in the background, a friend who revealed more of themselves when you truly looked, not with impatience but with presence. Reality, too, seems to respond to presence. It does not reveal itself all at once, but in relation, in dialogue, in participation. For Wheeler, this was not only a poetic musing, but a scientific proposal. He envisioned a self-excited circuit, a universe in which observers arise, make measurements, and thereby bring the universe into sharper focus. The cosmos generates life. Life generates observation. Observation generates reality, and reality generates cosmos in an endless loop. It is a vision of interdependence, where no part can be fully understood without the others. Whether or not this is the final truth, it carries a resonance. It suggests that to be alive is not only to endure within the universe, but to help complete it. Each glance, each measurement, each question asked is another brushstroke on the canvas of reality. The participatory universe is not something distant. It is unfolding in every moment you live. So tonight, as you rest, consider that you are not just drifting through a ready-made world. You are helping to bring it into being. The photons that strike your eyes, the sounds that reach your ears, the very awareness you hold, all are acts of participation. The universe is not a finished book you are reading. It is a conversation you are part of, a song you are singing even as you listen, and perhaps that is why the quantum realm feels so dreamlike. Dreams too are participatory. They shift with your attention, bend with your focus, weave themselves around the fragments of memory you bring. In dreams, you're both actor and audience, both creator and witness. Wheeler's participatory universe suggests that waking life may not be so different, that the cosmos itself is a dream written by its dreamers. Whether this is literal truth or simply a metaphor for mysteries still unsolved, it changes how we see ourselves. We are not merely spectators of existence. We are part of its unfolding, part of its restless conversation. Each of us is a note in the symphony, a thread in the loom, a listener leaning toward the fire as the storyteller shapes the tale. All through this quiet journey, we have wandered across scales. We have stepped into the smallest theatres, where photons hesitate between paths, where electrons blur into clouds, where atoms sing in uncertainty. We have drifted through stranger phases of matter, watched drumheads both beat and rest, and imagined clocks so precise they notice time flowing differently across the span of a human body. We have looked into leaves that harvest sunlight with quantum coherence, into birds that may see magnetic maps written by entanglement, into enzymes that slip through walls with tunnelling. We have paused at the border of consciousness, where theories suggest awareness itself may flicker with quantum rhythms. And finally, we stood with Wheeler's vision, a universe not finished but participatory, a story written as it is told. In all of this, one theme has lingered. The world is not separate from you. You're not an outsider gazing into a cage of mysteries. You are part of the experiment, part of the unfolding. Every glance, every measurement, every quiet act of noticing is a brushstroke on the canvas of reality. When you listened to these words, when you pictured photons passing through slits or leaves funneling sunlight, you were not merely learning, you were participating. The act of imagining is itself a kind of observation, and observation is what the universe weaves into being. To soften this thought, imagine sitting by a campfire at night. Sparks rise, embers glow, and a storyteller speaks. The story is not pre-written, but shaped by the listeners, by the way they lean forward, the way they sigh, the way they laugh. Each reaction nudges the tale, opening one path, closing another. The storyteller and the listeners are co-creators. The fire itself crackles in rhythm with them, as though the night participates too. That is the universe Wheeler imagined. Not a fixed script, but a story told together, each of us part of its telling. And perhaps that is why the quantum realm feels so strangely familiar. Its rules, superposition, entanglement, uncertainty, observation, are not only technical curiosities, but echoes of our own experience. We know what it is to hold multiple possibilities at once, like dinner undecided in the cupboard. We know what it is to be entangled, sharing silences with those we love. We know what it is to live in uncertainty, where not all paths are clear, yet life still moves forward. We know what it is to change simply by paying attention, to alter a conversation, a relationship, even ourselves, by the act of noticing. The universe, it seems, is not built of alien logic, but of patterns we have always felt, patterns written deep in matter and mirrored in our lives. That recognition is comforting. It means that even in the face of strange experiments and abstract theories, the quantum world is not distant. It is here, folded into every lamp that glows, every leaf that shimmers, every thought that drifts across the quiet of your mind. So as this journey comes to its end, pause for a moment and consider your own role as a co-creator. Each observation you make is a dialogue with the world. Each memory you form is the collapse of countless possibilities into one story. Each dream you have is a reminder that uncertainty and coherence live not only in laboratories, but in the private theatre of the mind. You're not only living in the universe, you are helping to write it. And what, then, is the meaning of this participation? Perhaps it is not about control, or power, or bending reality to our will. Perhaps it is about belonging, about knowing that the story is not indifferent to you, that your presence is part of the play. You do not need to understand every equation or grasp every paradox. It is enough to listen, to wonder, to notice. The noticing itself is what matters. In the quiet of your own room, with lights dimmed and breath slowing, you're part of the same conversation that began with the first photons, with the first atoms, with the first leaves catching sunlight. The tapestry of the cosmos is still being woven, and each of us adds a thread, however fine, with each glance and each question. And tomorrow, when you step into the day, you may carry a softer awareness of this. The lamp on your desk, the clock on the wall, the warmth in your tea, All are shaped by quantum rules. The world is not a rigid machine, but a shimmering haze of possibility, collapsing into clarity as you touch it, as you notice it, as you live it. So here, at the close of this journey, let us leave with one more question to carry forward. We have wandered through the quantum realm, through uncertainty and participation. Next time, we will ask, what if gravity itself vanished tomorrow? What if the force that holds your feet to the floor, that keeps planets circling stars, that binds galaxies into spirals, was suddenly gone? How would the universe respond, and how would we? Until then, rest in the knowledge that the universe is not complete without you. You're not just a listener, but a co-creator, not just an observer, but a participant. The story continues with you inside it, with you shaping it, with you dreaming it into being.